In this lesson, we look at the topic of nuclear fusion. Now, nuclear fusion is the process of combining light atomic nuclei, so hydrogen, helium, lithium, beryllium, and so on, the elements at the beginning of the periodic table, together into a heavier nucleus, something like lead or iron, nickel, and so on. Nuclear fusion is what powers the sun. So it is an ideal power source for us. In the sun, the process is called the proton-proton chain, and I'll explain why that is in a bit, or the PP chain. PP standing for proton-proton. Now the sun is mainly hydrogen gas. By mass, it's about 75% hydrogen gas, the lightest element on the periodic table. Now inside the core of the sun, it's about 15 million Kelvin. At that temperature, hydrogen atoms can't hold on to their electrons. They're bouncing around so vigorously that the electrons are stripped off. And a hydrogen atom without its electron is just basically a proton. So you have all this sea of protons surrounded, within this sea of electrons, all moving past one another, bumping into one another at the core of the sun at 15 million Kelvin. Now, at that temperature, protons, of course, being like charges, both positive charges, will try to ram into each other, but the positive charges repel and they'll be pushed apart. So millions of times in several seconds, you have protons trying to come together and getting pushed apart. But every once in a while, the protons actually get close enough that the electromagnetic force, while strongly trying to repel them, the nuclear strong force, which we'll talk about later on, works to hold atomic nuclei together. That force takes over and the protons merge. So you have a hydrogen atom or proton. The one means that there's, again, if you remember, there's no number down here, but that number would be 1. 1 represents one proton, which is hydrogen. The one at the top represents the number of particles in the nucleus, and of course, for simple hydrogen, it's just a proton. So you have a proton combining with a proton, forming heavy hydrogen, also known as deuterium. This is hydrogen with a neutron. So in this hydrogen, in this deuterium, it's an isotope of hydrogen. It's one proton, so it's still hydrogen, but it also has one neutron. So we've merged two protons together to form a single heavier nucleus, slightly heavier. In this process, a positron, which is an antimatter electron, and we'll talk more about matter and antimatter in the next series of lectures in lesson 3.5. A positron gets spat out, and another rare particle called a neutrino gets ejected. Now this neutrino is neutral, electrically neutral, very low mass, and can pass through huge amounts of matter easily. This positron goes on to collide with a nearby electron, forming gamma rays. In this process of combining two protons into deuterium, a positron, and a neutrino, about half, or 0.42 million electron volts, is released in energy. So fusion creates energy. Where does that energy come from? It comes from the missing mass. If you remember back to the relativity chapter, we talked about how E equals mc squared. If you add up the mass on the left-hand side of this equation, and you add up the mass on the right-hand side of this equation, you find the right-hand side of the equation has less mass. How much less? Well, you can actually figure that out. Plug this into the E equals mc equation, solve for mass, and it tells you how much mass is missing. It's a very small percentage, but enough that energy is produced. Then, now you've created deuterium. Now there's some deuterium floating around at the core of the sun. Most of it's still regular hydrogen, but a deuterium can come too close to a hydrogen. Again, these two things want to repel one another. They're both positively charged. But at the temperature in the core of the sun, they slam together with such energy that they can actually merge and form helium-3. Helium-3 is an isotope of helium. It's helium, so it has two protons at its nucleus, the second element on the periodic table, but it only has one neutron holding that nucleus together. In this process, another particle comes out which is called a gamma ray. That gamma ray gives 5.5 approximately million electron volts of energy released. So, more than 10 times what we had before in the previous step, more energy is released. Now you start building up helium-3 in the core. It's still mainly hydrogen. There's a little bit of deuterium floating around and a little bit of helium-3 floating around. The helium-3s, which again hate one another, they're repulsed by one another, but at the temperature in the core of the sun, they smash together. 2 helium-3s merge together to form helium-4, and 2 protons pop out. So there are 2 protons in helium-3 and 1 neutron. There are 2 protons in helium-3 here and 1 neutron. So we have 6 total nucleotides, right? 6 total particles in the nucleus. Here's helium-4, 2 neutrons. So the 1 neutron in each of the heliums both go into helium-4. And the 2 extra protons we have are spat out and start the process over again. In this third step, about 13 million electron volts is released. Now, overall what happens? There are many, many steps here. This process is constantly going on in the sun. Overall, 2 electrons combined with 4 protons. And in the end, if you ignore all the steps in the middle, the end result is you get a helium-4 nucleus out, you get 2 neutrinos out, you get 6 gamma ray particles out, and you release 26.7 million electron volts for every helium-4 nucleus produced. The sun takes hundreds of millions of tons of hydrogen and creates helium every second. That produces a tremendous amount of energy. That energy makes its way out through the surface of the sun, through convection and conduction, and then or convection and radiation, and then eventually breaks out and we see the sun shining. So much energy produced that the sun can burn your skin on a hot summer day 93 million miles away. The byproduct of nuclear fusion is helium. At least for the pp chain, here is helium. Now helium can be fused to create heavier nuclei, carbon, oxygen, and so on, through a process called the triple alpha process. Your book doesn't really describe it, but note that it's not just hydrogen that can be fused, it's all light elements. But the more massive the light element is, the less energy you get when you fuse it. So you can fuse helium, but you don't get as much energy as when you fused hydrogen. This would be an ideal energy source for people on Earth, if we could create this reliably in the lab. Sadly, we haven't really been able to. To create the conditions where nuclear fusion can occur, you need incredibly dense, incredibly hot gas. So hot that it would basically vaporize the container it was sitting in if it was allowed to bump up against the container walls. So a lot of engineering and a lot of physics go into trying to recreate a fusion type of a generator, reliable fusion generator that doesn't explode. We've built fusion bombs, the hydrogen bomb. We have nuclear weapons that utilize this to release a tremendous amount of energy. Most nuclear weapons though, most fusion bombs actually have a fission bomb at their core, an old atomic bomb that is much, much messier. And we'll talk about nuclear fission in the next lecture. So this process of nuclear fusion, while it's ideal, the nuclear waste that you produce is helium. The thing you breathe in out of a helium balloon at a birthday party, right? It's not a terribly dangerous substance. It's very neutral, chemically neutral. It doesn't want to bond with anything. Breathe it in. Well, you can't pass out because you're not getting oxygen. It itself is not toxic. So it's a nice thing to have as a byproduct for an energy source. But we haven't yet gotten it to be reliable. I think it's about break even now, or a little bit better than break even, which means that it takes as much energy going into creating the fusion event as you get energy out. So this, in short, is nuclear fusion. Hopefully, in the future, this can be done reliably and cheaply. However, right now, nuclear power does not mean nuclear fusion. Usually when people refer to nuclear power, they mean nuclear fission, which we'll talk about in the next video.